Hi, welcome students. I miss you and I want to keep teaching calculus. And one of the questions that I've had is, what is U-substitution? And this is actually would have been the next topic that we would have taught after we did separable differential equations. So if you didn't watch the first video that I made last week, or actually it was probably 2 weeks ago now, make sure you do that and make sure you've done that. This would be the next in-class instruction I would have done. There are also several videos now posted on the YouTube channel for the College Board, and if you haven't watched those and looked at those assignments, it's a good idea to start doing that as well. We're going to keep teaching. We'll get more details in the next week or so, probably from the school district, as far as what exactly this looks like in terms of grades and credit for all of you. But today I'm going to teach a lesson on U-substitution, and I'm also giving you some practice questions. So along with the notes that we're going to do together, the PDF that's posted on your assignment has several practice questions of U-substitution. This is an important skill in calculus, and U-substitution is a way for us to find antiderivatives or integrals of functions that are a little more complicated. And you can see that happens quickly when you do integration or backwards derivatives. Remember, integration means we're going backwards. So if you look at your notes on the top, I kind of introduced it already, but you should realize this is also a big theme in Calc 2, this idea of finding an antiderivative or a backwards derivative. It gets pretty complicated pretty quickly. So U-substitution is a great tool to have. So I'm going to look at example 1 with you. One way to think about U-substitution is finding kind of the chain rule backwards. We're kind of thinking about nested functions backwards and finding the antiderivative. We're going to start with a pretty simple example. So the first example is the integral of x plus 1 to the 40th power. So in a problem like this, I'm going to choose u. So we're always trying to figure out what is my inner function, and that's my u. So in this one, it's obvious u is going to be x plus 1. Now, when I define what my u is, I also have to figure out what du would equal. So in this one, du, so think about implicit differentiation. So the derivative of u we say is du. The derivative of x is just 1. However, this is in terms of x. Since we're doing it implicitly, we're going to say dx. Now I could have said 1 dx, but that 1 really is unnecessary. It's just plain old dx. So it's du in this one is the same as dx. So I don't really need the 1. I could just say dx is the same as du. So when I go back to the function up here and I think about what is the antiderivative of x plus 1 to the 40th power, we're going to say that this, so this is all side work ahead of time. And then if I look at this, it's going to be the integral. So instead of saying x plus 1, I'm going to say that's called u now. So u to the 40th power. And then where I have dx, I have dx right here. Dx is the same as du. So I'm going to replace dx with du. So now that I've defined a u and I've filled in du, I'm going to integrate this in terms of u. So remember, du means in terms of u when you do antiderivatives. So I know that when I integrate u to the 40th, it's going to be u to the 41st over 41 plus a constant. So remember, we knew that we had to have a constant because we don't know, it could be plus 1, it could be plus 2, minus 5, minus your favorite number. We don't know what that constant is. So now I've defined this in terms of u. My final step is to go backwards and fill in what u equals. So this is the same as, since u to the 41st, we know u is up here, x plus 1. So I'm going to rewrite this as x plus 1 to the 41st power over 41 plus a constant. Now this one is a simple example because the derivative of u is just 1. And you can see that when I substituted everything in, it went really smoothly. I didn't have any x's left. I only had u's, and the inner function, the derivative is just 1. So things get more complicated very quickly. So let's look at example 2. This one's a slightly more complicated. So example 2 down here, we have the antiderivative of 3x plus 1. And this is also to the 40th power. I forgot the 40th. So also to the 40th. So think about what do you think u should equal here? I'll pause a minute. So what is my inner function? That's our question we're asking. So in this one, our inner function is 3x plus 1. 3x plus 1. So I'm thinking about, okay, what is that derivative of 3x plus 1? So du equals the derivative of this. So the derivative of 3x plus 1 is 3, but I'm doing this in terms of x, so I need dx next to it. So we're doing this implicitly. Now I'm going to solve for dx. So if I solve for dx and get dx alone, dx would equal, so think about this algebraically. I would divide both sides by 3, so dx would equal du divided by 3. Okay? Now I'm going to go back up here, and I'm going, so this is all, whenever you do U-substitution, you have this initial work, this side work, kind of thinking before you do the problem. So then we go back to the original problem, and we rewrite it in terms of u. We know we've done the U-substitution correctly when I can rewrite everything without x's, only with u's. So in this one I have, instead of 3x plus 1, we're going to say it's u to the 40th. And then instead of dx, I'm going to, now I know in this one, in this example, I know that du over 3 is dx. So du over 3 is what I'm going to replace dx with. So du over 3 is the same as 1/3 du. So I could really just take that 1/3 and move it out front as a constant. So this is 1/3 integral of u to the 40th du. So then we have to find that antiderivative. We haven't done any antiderivatives yet. So then this is the same one we just did. So the antiderivative is going to be 1/3, and then it would be u to the 41 over 41 plus a constant. So if I multiply 3 by 41, let's see, that's going to be 123. So I'm going to have, this is going to be 1 over 123. And then instead of u, I'm going to fill in u with 3x plus 1, because we're going to go back to the x for our final answer. So 3x plus 1 to the 41st plus a constant. So that's written as our final antiderivative in terms of x. So feel free to send me questions about the examples as you watch this, or post them on Google Classroom, and I will try to answer them the best I can. But we're going to do one more now. So example 3. So let's take a look up here at example 3. So this takes it one step further. So in example 3, we have find the integral of x squared minus 5x plus 1 to the 40th power. And then we also have this 2x minus 5 dx. Okay. This part is important, and we'll look at that in just a second. So when I look at this, you might think, well, wait a minute, Mr. Tan, I see this function and I see this function. What's my inner function? Well, so we want to pick a u such that the du is part of the problem still, so we can eliminate that derivative. So the first one and the second one were easy because the first one, the derivative was 1. The second one, the derivative was 3. Those are just constants. This one, the derivative of this, if I look at this and I say, well, it looks like this one is my u. So u equals x squared minus 5x plus 1. Now the reason I'm picking this one for my u is it's to the 40th power. This one doesn't have a power. That's one of the clues I see. Also, I'm thinking ahead and I'm thinking, I know the derivative of this is going to be 2x minus 5. Ooh, it's right there. It's staring us in the face. So and when I think about this one, the derivative of this is just 2, and I still would have this to deal with. It's not going to work out nicely if I pick that one as my u. So I'm going to pick this one as my u. So when I do that, I get that du equals 2x minus 5. Now, I also need, now if you think about it, I could have had dx here and dx here. The best way to do that is just write dx out there, outside. Because you would have 2x dx minus 5 dx. I'm just going to put dx right there. Now, just like before, we're going to get dx alone. So dx alone, so dx is going to be du divided by 2x minus 5. So here's all my side work, just like the other ones, that initial substitution. Now we're going to go back to our original problem and write what we have when we integrate. So we have the integral. So all of this stuff right here is our u. So it's going to be u to the 40th, and then I don't have anything for 2x minus 5. I'm just going to write 2x minus 5, because I didn't call that u. But then for dx, I did solve, and I found that dx is du over 2x minus 5. So I'm going to have du over 2x minus 5. Now watch the coolness that happens here. So I have a u here, I have 2x minus 5, but then I have divided by 2x minus 5 here. So what's going to happen to those 2x minus 5s? If we were in class, you would have all said, they're going to cancel, Mr. Rattan, so I'll just cross them off, right? Okay, so now when I rewrite it, I still am left with just u to the 40th du. So I have all in terms of u. Now, remember I said we know that we did the u substitution correctly if when I rewrite it in terms of u, I've gotten rid of all the x's. I can cancel all the x's. And this is what I mean. I could cancel these x's. That's my clue that I did the u substitution correctly. So if I keep going with this, I'm going to end up with u to the 41 over 41. This is the same problem as what we saw in all the other examples, just different u's. So if we keep going here, this would be equal to, so I'm going back to what u is in this one. It's x squared minus 5x plus 1. So this is all to the 41st, all over 41 plus a constant. So that's the third example. Now, each of these problems gets a little more complicated. So there's a couple at the bottom there, 1 and 2, for you to try. I think what I'm going to do is I would recommend right now that you pause the video, try problems 1 and 2, and then I will work through problem. Try 1 and 2, and then check with your friends, see if you're getting some of the same answers. Virtually, maybe send each other answers, or I will post a key eventually, and we could check answers. Maybe I'll do that. And then finally, on the back, there's several different examples of problems for you to try. I think at this point, I'm going to have you pause the video also, and I will, if you start back up, I'm going to work through question 1, and yeah, maybe question 1 and question 5 on the back for everyone to have a few more examples that are slightly different. So pause if you haven't. Okay, so now I'm going to work through questions 1 and 5 on the back side. Hopefully you've had a chance to try a few of these on your own. That would be best. If we were in class, I wouldn't just jump right to these. I'd give you some time to wrestle. So let's look at question 1 on the back. So question 1 on the back is the integral of x squared e to the 4x cubed dx. Now, with all these problems, the first question is, what do I use for u? What should u equal? So you're always thinking about what seems more like the inner function. And also, whatever I pick for u, I want to make sure, whatever I choose for u, I want to make sure that du is also in the problem so that when I do the substitution, the x's cancel. So in this one, I have kind of a few options when I look at it, maybe x squared or maybe 4x cubed. Well, which one, when I take its derivative, sort of gives me the other one? And it would be the 4x cubed as my u. And that one also is the inner function. So u is 4x cubed. Du is going to be 12x squared dx. So if I solve for dx, dx is going to be du over 12x squared. So now, if we rewrite this, so here again is the side work. This will equal the integral of x squared e to the u, and then I have du. So I'm substituting instead of dx right here, and this is a step sometimes students miss initially. I'm putting, instead of dx right there, I'm putting this in to dx. Okay, so I'm going to have du divided by 12x to the second. Now, you can see that the x to the seconds cancel. So I'm going to take that 12 and move it out front as 1/12 integral of e to the u du. So I know that the derivative of e to blah is e to the blah d blah. I know the integral of e to the blah, or e to the u, is just e to the u. So this is going to be 1/12 e to the u plus a constant. And then I just go back and substitute in what u equals. So I'm going to have 1/12 e to the, so u equals 4x cubed plus that constant. And that would be my final answer for number 1. Number 5 is a little bit different, so I want to do that one as well with you. And then hopefully you'll have enough tools to do the rest. I will work on a key and probably put that up in the next few days. I want to tell you too, on those back practice problems, not all of them need U-substitution. So if you look at them, I see that one of them you could integrate no problem without U-substitution. Sometimes what happens when students do these problems is they think that every problem needs U-substitution, just like with chain rule. But sometimes you have problems where you don't have a function kind of nested inside a function. So I'll let you try to figure that out. But let's jump to number 5. That one definitely does need U-substitution. So number 5, it's sine of x in the top divided by 1 plus cosine of x dx. So this one is a fraction. And when you have a fraction, we want to think about what's in the top and what's in the bottom. In this one, I can see, well, when I take the derivative sine, I get cosine. Also can see that when I take the derivative cosine, I get negative sine. But one of the things I also notice is I have the 1 plus part here. And this one's going to work out a lot nicer if I just take this whole bottom, and that is my u. So you'll see this sort of a problem a lot where you have the derivative of the denominator gives you the numerator, because I know derivative of 1 is just 0. So I'm going to say u in this one is 1 plus cosine of x. So then du is equal to, so the derivative cosine is negative sine of x dx, and then dx is equal to du over negative sine of x. So now I'm going to use that substitution to rewrite this. I'm going to block the side work off. And so this would equal the integral. So I still have sine of x. So sine of x divided by u is in the denominator. So I substitute for u, and then I substitute for dx. So where I see dx up there, I'm going to write what I got down here. So dx is the same as du over negative sine of x. So this is going to be times negative sine, du over negative sine of x. Okay, again, I know I did my problem right or correctly if I can cross off my X problem. Hey, I'm finding different colors of chalk. My kids have all these different colors of sidewalk chalk, and I can put them to use. That's cool. All right, so this will end up being the integral of, now I have that negative sign, so I'm going to actually just set the negative out front. It's just like a number. So negative, and then it would be du over u. You might be a little rusty with this, but remember, when I do the derivative of natural log, I get 1 over, so the derivative natural log of blah is 1 over blah d blah. Well, this one, so the antiderivative of du over u is just the natural log of u. So in this one, the antiderivative is just going to be negative ln of u plus a constant. So notice I put the absolute values here because the absolute value, I can't take the natural log of a negative number, and so that ensures that my input is defined. And then I'm going to go back and fill in u, so this is going to be negative ln absolute value of, so I'm going to fill in the 1 plus cosine of x, and then plus a constant. And that is my final answer. So to recap, in all these problems, we always choose a u such that du is part of the problem, so that when I rewrite it, I'm going to end up with just u's. And then I integrate it in terms of u, find the antiderivative with just u, then I fill in what that u equals in terms of x to get my final answer. So this process is called U-substitution. It takes practice, so you're going to need to do these practice problems. Look for a key in the next few days. Also, don't hesitate if you have a question you want to send me on Google Classroom or over email. And then finally, if you want more practice, there's tons of it online. If you search U-substitution practice or watch other YouTube videos from other instructors, you'll find a ton of resources. So in this situation, it's really up to you how well you want to understand this stuff. If you really go after it and look for resources, there's lots of stuff available. But I'll provide as much as I can as well. So in closing, I have to say I'm heartbroken that we can't be together in person right now. And I'm heartbroken for the seniors that we're not going to have time in class anymore. I'm really missing you guys, and I know you're missing being at school. So keep your heads up and stay healthy, and hopefully we will cross paths soon in person. So take care and look for that key. See you guys later.